All right, we're live. Okay. Yeah, so I guess we can get started then. Can you guys hear me? Yeah, I think it's good. All right, so thanks so much, guys, for coming today. I'll be kicking off our 1041 revision seminar, presenting on parts regarding probability and random variables, and Gerald will take us through the statistical inference part of the course. I think how we're going to do this, I'm just going to go over the slides, go over the questions that we are meant to answer. And you know, if there are any questions that you guys have, feel free to let me know. And yeah, sorry, let me just. Oh, how do I scroll down?
You can just press the arrow.
Okay. Okay. Okay, so. Yeah, so let's just get started with this. So the first part that I'll talk about is the descriptive stats part of the course. I'll just go through this really briefly because it's a bit of a more minor section of the course and it's relatively straightforward. So we start off by talking about the different types of data that we have. In the real world, there are two types of data. There's quantitative data and categorical data. Quantitative data, it's basically data where the values are numerical and where arithmetic makes sense. So if you have a quantitative data, you can do addition, subtraction, you know, all these arithmetic things. And examples of this would be like your height and your WAM. Categorical data is data that exists naturally in categories. So these are stuff that in their natural form, you might see them in one or more categories. So for example, colors, genders, yeah, that sort of stuff. So the reason why it's important to be able to distinguish between these two is because when you are visualizing and summarizing data, it's highly dependent on the type of data that you have, so quantitative or categorical. So let's just quickly take a look at a numerical summary of a categorical variable. So this is a table of frequency. I think this one is pretty straightforward. You know, you're just counting the number of instances each one takes place. So for example, category A right here. Oh. Category A right here. Sorry, give me a second. Category A right here, as well as category B. Yeah. So this is where you just count the number of instances each category appears, and you just find the percentages. So the next numerical summaries that we have, we'll be talking about measures of location. This is for quantitative variables. So essentially, when you have a bunch of quantitative variables, or at least a variable that's quantitative, you want to see where is the center of that data. And there are two things you can look at to see where the center is, which is essentially the mean and the median. The mean is just the average of the quantitative variables. So you just take the observed sample, you compute the sum of all the observed variables, and you just divide it by the total number of observations. Meanwhile, the mode, it's another measure of location, another measure of the central location of your data, and it's a little bit different to the mean because for the median, what you would do is you would arrange all the values in order, and then you take the middle value. The good thing about the median is that it's robust to outliers, unlike the mean. And when I mean robust to outliers, I mean that even if you have a very large data or you have a very small observation, it doesn't matter because your median would still stay the same. So for example, if these were our observed values, like 1, 3, and 5, then you would see that your median is 3, right? And it doesn't matter if it's a very small value, like 1 million, like minus 1 million here, or maybe 100 here. It's still going to be, it's still going to be 3. That's going to be your median here. So the next part we'll talk about is now measures of spread. So we talked about what the central location of your data is, but the second thing that we want to look at is how spread is your data around your mean. And there are two ways to look at this. So firstly, we have the standard deviation. Literally, if you see the formula here, it just measures how much the data varies around the mean. And if you look at the formula, you can see indications of this because, for example, right here when you have the observed value, it's just taking the difference between the observed value and the mean, and you're just squaring it. So you're taking all these sums of squared differences, and you're just dividing it. So this is why it can kind of tell you how much your data is moving around the mean. The second measure of spread that we have is the interquartile range. So what this is, it's just the difference between the third quartile and the first quartile. And like before, comparing between median and mean, the IQR, the measure of spread, it's robust to outliers as well. Okay, so this is the very important part here. Robust to outliers. Wish I could draw this better. Okay, So numerical summary of quantitative variable. There's one more that I'd like to talk about really briefly. It's the 5-number summary. What this is, it's essentially just the minimum, the first quartile, the median, the third quartile, and the max. And this is really useful, see, because usually when you're exploring new data, this is the first thing that you look at. You look at the 5-number summary and you just get a feel for, hey, is my data, like, what does my data look like, right? Cool. So after this, I'm just going to quickly go through several images and summaries, so graphical summaries of variables. So the first one is for bar charts. Yeah, this is relatively simple here. This example right here, you have 3 different types of species, and this is just the average length for each species. So it's just a very straightforward way, bar charts. The next one we'll talk about is histogram. So the difference between the histogram and the bar chart is that while the bar chart is used for categorical variables, the histogram is used for quantitative variables. So what they do is for the quantitative variable, you group it up into ranges, right? So in this case, we're talking about response times, and they're grouping up into ranges. So maybe 0 to 1 hour, 1 hour to 2 hours, 3 hours to 4 hours. And you're just counting the number of instances that fall within that range. That's how you get this kind of graphical display here. It's really nice for seeing what the shape of your data looks like. Okay. So the last part I want to talk about when it comes to summaries is going to be the box plot. So the box plot, again, is a graphical summary of a quantitative variable. And what it does is it essentially lets you look at several things at the same time. So we'll just go through it one by one. So here's the box plot right here. Anything outside of these whiskers right here, this left side and this right side, they are called outliers. Essentially, these are data points that don't really make sense when you look at the other observed values from your sample. How you define an outlier is that if it's less than quarter 1 minus 1.5 times IQR, or if it's greater than Q3, the third quartile, plus 1.5 times the interquartile range. Essentially, anything within this range right here, it's considered an outlier. The left and right whisker right here, this is the minimum and maximum, in the sense that this is the minimum and maximum of your data that makes sense, that is not an outlier, okay? So this is where you kind of draw the line and you say, hey, anything less than this minimum value is an outlier. Anything less than this maximum value is an outlier. Then we have 3 important lines here in the middle. This is the first quartile, the median, and the third quartile here. So yeah, the reason why this is a very handy kind of graphical tool is because you know how I talked about the 5-number summary? It helps you see what different numbers are for your different measures. Right now, this is kind of like a graphical depiction of it, right? Because you can essentially see where your first quartile is, where your median is, and where your third quartile is, as well as like which data points make sense and which data points don't make sense. Cool. Any questions about this one? Great. So I think then we'll move on to the next part here, because this is definitely a more interesting point of discussion, probability. So we'll start off with some simple definitions. You don't have to note this down, but I'll just quickly go over it for the sake of it. So an event, it's an individual outcome. A sample space is the set of all possible events. We normally denote the sample space as S. And the probability of an event is essentially the probability that a particular outcome happens from that sample space. The whole idea of probability is that you're defining what is possible and what's not. And you're just trying to see, hey, out of all these possibilities, what is the probability of this particular possibility happening? Or maybe what is the probability of that particular probability happening? And that's why we have definitions like sample space and events. Okay? We use this notation here, PA, to denote the probability of an event. So there are a couple of rules about probability to make it make sense. You don't have to memorize like what these rules are, but essentially you just have to know this is why probability makes sense. So firstly, it's bounded by 0 and 1. What this means is that you won't have a probability that's 1.15, right? That doesn't make sense, because 1 means that it's absolutely gonna happen, and 0 means it's absolutely not gonna happen. There's nothing about those two. Next is that it's covering. So what this means is that the probability of the sample space is 1. This means that the probability of all your events happening is 1. Well, that makes sense, right? Because you're defining what is possible to happen. And if all of these events are happening at the same time, it means that the probability is just 1. Then we have this additive rule right here. So PA or B equals to PA plus PB minus PA and B. Now, you might not be used to seeing this final term here, but we'll talk a little bit more about this final term here. But just take my word for now that this is the typical formula that you have for the additive rule. And the last one here is the complement rule that states that anything that is outside of that particular event is just 1 minus the probability of that event. Okay? So I think those are just a very brief look at the probability rules, and now I just want to talk a little bit more about the additive rule. So like I mentioned before, the term that you saw here at the end, where it's minus PA and B, you might not be used to seeing that because sometimes it's not existent, this particular term here. And we'll go into cases that's such true. But in general, if you're used to seeing this right here, PA or B equals to PA and B, just remember that this is generally not true. Like it's not always true in all cases, and there are special cases where this is true. So you just have to use this fact right now. PA or B equals to PA plus PB minus PA and B. The next concept that I'll talk about is conditional probability. Yeah? So one useful fact about probabilities is that you can take into account what things have happened already. So for example, when you have two events, events A and events B, the conditional probability of A, so A given B, is given by this formula right here. PA, oh, if only I could draw this a bit better, but PA or B, sorry, PA given B equals to PA and B divided by PB. I think when I was learning about these concepts, I was pretty confused, like which one goes where. One thing to remember is that the second term always goes bottom, okay? Just always remember that. Whatever is given something, so A given B, if it's A given B, then B is always going to be the one at the bottom here. And the top part is always going to be the AND. That's how I remember it. So if let's say we have P, let me try to draw it out. Can I draw it out? So if we have, oh, it doesn't work. So if we have, anyways, if we have like PC and D, sorry, PC given D, then the D would go to the bottom and C and D would be on top. The usefulness of this is that it's slightly different from regular probabilities because now you're saying that, hey, what is the probability of A happening given that we already know the probability, given that we know that B has already happened here. And this is useful in cases where you have to draw tree diagrams and stuff. And we'll show you how this looks like in a past exam question. So with this, we're going to transition to our first exam question of today. This is from 2018 semester 2. So assume that 20% of people have a flu immunization at the start of winter. Suppose that 5% of people who have a flu immunization will contract the flu, and that 30% of those who do not have a flu immunization will contract the flu. What proportion of people will contract the flu? Alright, that's a lot of information, but let's break it down. So I have my whiteboard here. I'm just going to switch it. Hopefully that's right. Is it switched? Okay. Yeah. So I'm just going to write here. So we had that. Oh. Sorry, I'm kind of new to using this thing. So just give me a second while I work this out. Okay. So the first bit of information is that the probability of flu is, what was it? The probability that you would get a flu. Oh, sorry. The probability that you'd get immunized. So the first one is probability of immunized. Oh my god. The probability of you being immunized is 0.3. That's the first bit of information that you're given. The second information that you're given is 0.2. Oh my god. Okay. Bear with me, guys. Okay. So the probability that you'll be immunized is 0.2. Then the probability that, suppose that 5% of people who have a flu immunization will contract the flu. This means that the probability that you would get flu, given that you're immunized, is only 0.05. Okay, so let's write that down. What that would look like would be P of F, so flu given that you're immunized, it's just going to be 0.05. Right, that kind of makes sense, right? Because if you're immunized, then there's a lower chance that you might get flu. And suppose 30% of the people who do not have a flu immunization will contract the flu. So this means that the probability that you get flu, given that you're not immunized, remember the complement rule, this is how we denote it here, this is going to be 0.3. So this is the kind of information that is available to us right now. Okay. So our question right now asks us to find, what is the probability. Okay, this is, sorry. Alright, let me just fix that right here. Why does it keep... Alright, this is a bit problematic. Given IC. Yeah, so what we're trying to find right now is the probability that you would get the flu. And how I would recommend for you to tackle these types of problems is by doing a tree diagram approach. So let's just zoom in another thing here. So it's really great for you to graph out this information to find. So we have a couple of branches that are happening right now, okay? So the first instance right here that I can tell is that you might, any random person, you might be immunized and you might not be immunized. And the probability of you being immunized is 0.2, remember we recall? How about the probability that you're not being immunized? Remember with our rule, we are saying that anything that's the complement is just 1 minus that probability. So you might be 0.8 right here. That's the probability that you're not being immunized, okay? Now, given that you are immunized right here, given that you are immunized, your probability of getting flu, okay, this is going to be 0.05. That means for the same branch right here, given that you are immunized, the probability that you are not going to get the flu is going to be 1 minus that, okay, 0.95 right here. Now, let's just repeat the same steps for the next case, which is you not being immunized. If you are not immunized, the probability of you getting flu is 0.3. So that was given from our question. So the next thing to find is the probability that you will not get the flu if you are not immunized, 0.7. Right, great. So it's great that we have this kind of depiction here because now if you're trying to find like the overall probability, it's really easy. So if you recall, the formula for conditional probability is this. Probability of f and I over probability of I. Okay, so the probability of f and I equals the probability of I times probability of f given I. And if you look at the branches here, this is exactly what's happening. If you follow along the branch, this first branch right here, so if you follow along in that direction, you would get 0.2 times 0.05. And this is essentially the probability of you being immunized and getting the flu. So in our question, if you recall what the question is, we are trying to find, it's moving again, yikes. Oh. We are trying to find what the probability of you getting the flu is. Well, the probability of you getting flu is that you're getting flu and you're immunized, or you're getting flu and you're not immunized. So it's just the sum of these two probabilities right here, which is the first one, this is, what is it used for? Sorry, Gerald, could you help me? Like it just like switched up to a keyboard. Like it just shows this thing here. Okay, thank you. Yep.
You can also move it with your finger if you want.
Okay.
Probably easier.
Oh yeah, that's right. That's easier. Thank you. Okay, so, it's making so much mess. Okay, anyways, so we are trying to find probably F right here. Yeah, so the probability that you are gonna get flu, it's gonna be the probability of you getting flu and being immunized, or the probability that you are not getting flu, and you're getting flu and not immunized. And to get this final probability here, all you have to do is you have to find the branches. Find the branch that leads to the right thing. So you can see that F is over here. Just find the one that leads to the F. So we have the first branch, which is 0.2 times 0.05, and that leads to the F right here. The second F that we have would be 0.8 times 0.3. And that's how you get your final answer here. You just have to find all the branches that lead to F in the end. Okay? So this would be 0.2 times 0.05 plus 0.8 times 0.3. And if you sum that up together, that should give you 0.25. Now, this kind of question, it's only like a 3-mark question if I recall, but it's essentially quite easy marks because you can just draw it out, follow the branches, and you would get the right answer. The only tricky part would be trying to understand what each branch represents. But if you keep in mind what the definitions of conditional probability are, you should be able to get this pretty easily. Okay, cool. So that's our first question here. If I'm going back to the slides, I actually have like a written example right here. This is a very formal way of saying it. I'll share the slides with you guys later on, but we'll just skip over this. So I just wrote a bunch of things about how you might write this in terms of mathematical notation. But I think for the purposes of this course, if you do a tree diagram and you just write down the probabilities, it should be sufficient. There we go. Cool. So moving on to the next concept right here, we're going to talk about the notion of independence. So for events A and B, we say that A and B are independent if either the probability of A equals the probability of A given B, or the probability of B equals to B given A. Essentially, what this means is that the probability of A happening doesn't change regardless of what the probability of B is. Same thing with B. The probability of B happening does not change given what the probability of A is. Okay? And that's why they are called independent events. They just don't depend on each other. The really nice thing about this is that if you rewrite the formula for conditional probability, you will have this particular formula right here. And I love this formula because it makes life a lot easier. The probability of A and B equals the probability of A times probability of B. Okay? This is like another way to look at independence formula aside from these two. The first one and the second one here. So let's just kind of see this in action with another past paper. So this is an older one. I don't expect that your questions might be similar, but let's just look at it for the sake of it. So a fair coin is flipped twice. Okay, we're flipping 2 coins. On each toss, the probability of heads is half and probability of tails is half. All right, straightforward. Let A be the event that the first flip is H. So the first flip is heads, okay? And let B be the event that both flips have the same outcome. Using the definition of independence, prove that events A and B are independent. Okay? So remember again that our definition of independence comes from two different things. Either you use the one down here or you use the one up here. And for this particular question, we'll use the one up here. So we are trying to show this. PA given B equals to PA, or PB given A equals to PB. So when you're doing these kinds of questions where you need to prove something is true or something is not true, you just have to try to look back again to what the formula tells you and try to prove that, that it leads back to this particular equation. So what you would do here, I think, if I'm not mistaken, you would end up trying to find PA and B. Then you will try to find what PA is, and you'll try to find PB is. And when you have all this information together, you just plug it into the formulas and see whether it makes sense. So let's just look at that. So let's start with probability of A. So the probability of flipping a head on the first go, it's just half, right? Because at any time when you flip the coin, it's going to be half heads and half tails. So the probability of A is just going to be half. Then we see that the probability of B. So what is B? B is the event that you get 2 of the same thing when you flip the coin. So there are only 2 cases where that can happen, right? Tails, tails, or heads, heads. Which is why the probability of B happening is also half. Okay? Because we have 4 different outcomes here where it's like head, 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 tails, tails, head, and tails, tails. And the one that suits our criteria is going to be heads, heads, and tails, tails. So the probability of B is simply given half. So this is great. So we figured out 2 components already here. We've already figured out what PA is and what PB is. So now we have to find what is PA and B. Well, luckily for us, the question has made our life a lot easier here. Remember that remember that A is just looking for the outcomes where head is flipped first, right? So if you're looking at the probability of the events that suit the criteria of B, it's going to be head, head, and tails, tails. So out of these 2 probabilities, only head, head also fulfills the criteria of A. Does that make sense? So we again, for B, we have 2 outcomes right here, which is H, H, and TT. We are trying, if you want to find the probability of A and B, you have to see, like, out of these 2, which is the one that fulfills the first flip being H, and it's actually only one over here. This means that the probability that that your coin lands on head first, and both of the flips having the same outcome is going to be 1 over 4. Okay, so it's only one of 4 cases that you would have that happening. So it's written down here. The probability of A and B happening together occurs when we have the outcome HH. Hence, we have P A and B equals to 1 over 4. Now, at this point, I might pause. Like, did you guys get that part here and why this is like 1 over 4? Yeah? Alright, great. Cool. So with this, now that we have our elements of our equation, we just plug it in. Yeah? We just want to see that PB given A equals to PA and B divided by PA. So PA and B, this is 1 over 4. PA, this is 1/2, which we found. And we solved to find that this is equals to half, which is equal to PB. Done. This is enough to show your independence. So in case you ever find a question like this in your exams, just remember again what the formula you're trying to prove, find all the relevant elements and just plug it into the formula. If the formula holds where it's like PB given A equals to PB, or if you flip it around PA given B equals to PA, then that means you finished the question. You're good. Cool. So I'm going to end off the topic of probability by a brief note on mutually exclusive events. The idea behind mutually exclusive events is that these are two events that just the probability of them happening at the same time is 0. So a very good example of this would be, let's say you're just given any probability right here, like the probability of let's say any event G. Like G can be any kind of event. Like let's say the event of you guys coming to the math seminar. Okay, that means the complement of this is going to be you guys not coming to the math seminar, right? Now, if you have a complement and an event, these two things are always mutually exclusive because there is no way you could be in the seminar and not in the seminar at the same time. And that's how you can kind of think about mutually exclusive events here, that there is no way that they can happen at the same time. If I were to give you an example for the previous question, the one on flu immunizations, you can't have flu and not flu at the same time, right? So that's the kind of like same idea here. Now, one common misconception that students make when you're talking about mutually exclusive events is that it's often confused with independence. It's not the same thing, okay? Two events being independent, they can still happen at the same time, but it's not, so that's why it's not independent events does not equal mutually exclusive events. So if you're looking back at our additive rule here, if you remember, PA or B equals to PA plus PB minus PA and B. So the case where you would have PA or B equals to just these two terms, okay, and you exclude the last term here, only happens when you have mutually exclusive events. Because our definition of mutually exclusive is that the probability of A and B happening at the same time is 0. Okay? So this is where you would get PA or B equals to just PA plus PB. So if I'm going to wrap up all this information in the next slide here, just to let you guys see the difference. If A and B are independent, you would have PA times PB equals to PA and B. Or you would have PA equals to PA given B. Or you could just flip the other way around here. Okay? These are the definitions of independence. If A and B are mutually exclusive events, then you would have PA or B equals to PA and B. Okay? So it's kind of a nice way to remember this stuff. To remember the formulas here. Cool. Any questions so far? No? Okay, great. So we'll move on to the next topic, which is discrete random variables. Again, I'm going to start this off with a little bit of definitions. Just read this really briefly. So a random variable, it's a function that takes an outcome from a sample space and maps it to a real number. We'll give you an example of what this means later on. A discrete random variable is a type of random variable that takes a finite set of values, meaning that you can count each outcome in the sample space. So for example, the number of heads when flipping 3 coins, right? You can count, you can either have 0 heads, 1 head, 2 heads, or 3 heads. There aren't infinitely many heads, or there aren't like decimal points like 3.15 heads. Doesn't make sense. Another example, the number of people drinking coffee on a particular morning, right? That's also countable. Number generated by a random number generator. This is also a discrete random variable. So now that we understand like what a discrete random variable is, the next thing to talk about is probability distribution function. And this just tells you like what is the probability of you observing a particular value from that random variable. So for example, if x1 is the event of a 6 being thrown from a fair die, you know how a fair die, it can be like 1, 2, 3, 4, 5, 6. then the probability of the fair die being 6, that's just 1 over 6. And this p right here, this p right here, this is the probability distribution. Like it just tells us like, hey, what is the probability of this event happening? Same thing here. If your random variable is going to be the head being thrown from a fair coin, then the probability of this random variable being heads, the side of the coin, it's going to be just half. Okay, that's the probability distribution. Now, I guess the more important part about probability distribution, or not more important, but equally important part, is just learning how to compute the means and the variances, because this is what you might typically use in exams. So, the mean of a discrete random variable, it's just the sum of the multiplication between the observed value, so this xi, and the probability of that observed value being observed. You might sometimes hear this as expected value, mean value, but either way, this is just a very nice formula to put it together. If it looks a bit complex, don't worry, we'll go through an example of what this looks like. Right here. So let xi be the number of cars owned per household. Okay, so number of cars, this is our discrete random variable here. So this is going to be our x right here. Okay. No. Okay, here we go. This is going to be your x. And these small things, these are your observed value. This is your x1. This is going to be your x2. It's going to be your x3. And so on. This is going to be your x4. That means this probability here, this is the probability of x equal to x1. Okay. X equals to x2. And so on and so forth. So if you're asked to find, like you're just given this table right here and you're asked like, hey, what is the mean number of cars owned? Then you can just plug in the formula that we already talked about here. So if I'm going to write it down, it's going to be the sum of the probability of x equals to xi multiplied by xi. And here's an example. So this right here, 0 right here, this is x1, right? And this is the probability of x equals to x1. X equals to x1. Then plus 1, which is x2, so the other observed value, you can have 1 car, times the probability of the cars being only 1. Then 2 times the probability of the cars being 2. And 3 times the probability of cars being 3. So this is how you find the mean number of cars, and you would get this value in the end right here, 1.62. Okay? So we're going to regress a little bit here, and we're going to talk about independence again, because I think it's a pretty important note. So you can actually talk about independence in a sense for random variables too. It's a little bit different from probability, but the idea is that if two random variables are independent, then they just don't influence each other like probability. So for example, if you have a die and you have a coin, if you toss the coin and you roll the die, like, whatever value that the die takes, it's not going to impact the coin, right? And same thing, whatever value the coin takes, it's not going to impact the random, it's not going to affect the die. And the reason why we're talking about independence right now is because the notion of independence for random variables, it's very important when you talk about variances. So let's look at that in a bit. Anyways, so going back to the course, there's a couple of more rules about expected values. Just now we learned about how do you compute an expected value, right? Well, actually, there's also several rules about expected values. So let's say that we have a new random variable, y, okay? Y is a new random variable that is a combination of, that makes use of x, which is a random variable that we already know. So essentially here, the expected value of y, if you're given this formula, okay, the expected value of y is just going to take out the a and the b right here. Okay, so the expected value of y is going to be e ax plus b equals to a times expected value of x plus b. So this is going to be a times the mean of x plus b. Okay, so this right here, expected value of y, you see the a and the b here, these are constants, right? Just remember that you take out the constants, you can treat the ex over here as like an algebra or something like that, and you'd get this formula right here. Now, this is really handy, right? Because let's say you already calculated the mean of x. This means that if you have a new random variable y that makes use of x, you don't have to like make a new table and calculate the probabilities and calculate everything again. No, you just take the mean of x, you plug into the formula that makes y, and you would get the mean of y. So we can see how this is useful here. So let the random variable x represent the number of cups of coffee that Jane drinks on a normal day. This is from 2020, by the way, final exam. Below is the probability distribution of the number of cups she drank over the past year. So we have 0, 2, 5, 8 cups per day. and the probability is 0.4, 0.4, 0.1, 0.1. So the first question asks us to calculate the average number of coffee cups she drinks per day, mu x. But I'm not really interested in that because we talked about how we calculate the means already, right? You're just taking the xi's, Oops. Yeah, so you're just taking the xi's, you're calculating by the probability of x being xi, right here. You're just repeating this entirely, and you would get this value right here, 2.1, if you calculate from this table here. What's interesting is that, again, look at this. If you have a new random variable y that is made out of a linear combination of x, you don't have to make a new table, right? You don't need to make a new table anymore. You just need to use what you already found from the first question, which is mu x. So the question asks you to compute what is mu y. And look at this. All you need to do is you use the formula. So remember, you just take out the constants. So this would be equals to expected value of y. It's going to be 5 plus 9 times expected value of x, based on the formula that we had. So if you already compute mu x is 2.1, you just have to plug in 2.1 here. And you can see how it goes over here. Mu y equals to 5 plus 9 times mu x equals to 5 plus 9 times 2.1 equals to 10.5. So that's the very useful part of having the rules of expectations. I would note though that you guys probably want to be careful when you're doing your exam, because these type of questions, if you get your part A wrong, that means your part B would be wrong as well. So just be kind of careful when you're computing the mean. So now we can talk about the variance of discrete random variables. It's defined by this formula here, and I think essentially what it is, like before, the variance is a measure of spread, right? Think of it as how much is my random variable changing from the mean. And this is how you take the variable, the formula. You just take the observed values right here, so the small xi's. You take the difference with the mean of the x, and you just square it times the probability. I think showing the formula might be a bit confusing, but let's just look at how it's used as an example. Yeah, just let you guys copy that down first. Yeah, are we good? Yeah. Okay, cool. So let's just look at how this might apply to our same question. So remember Jane, Jane likes to drink a lot of coffee. So just now we already computed mu x, okay? We already found what mu x is. Now we are asked to find the variance. Our formula is this. You're taking the value of xi minus the mean of x squared multiplied by the probability of x being xi. So we just plug into the formula. Remember, mu x is 2.1. So, I'm sorry, this is just such a mess. Okay. There we go. Getting the hang of this, I think. Anyways, so recall that we had mu equals 2.1. So we just plug in the formula. So, xi, we start with 0. 0 goes here, okay? Minus the mean, which is 2.1, so minus the mean, and 2.1 goes here. Square that, okay, and multiply by the probability, 0.4. So that's the first term right here. Then you take the next sum. 2 goes here, minus the mean, which is 2.1. You square that, and you multiply by the next probability, 0.4 right here. Okay? 0.4 right here. And you just repeat that, essentially. You just take again 5 minus 2.1 squared times 0.1 plus 8 minus 2.1 squared times 0.1. So I think it's relatively straightforward as long as you plug in the numbers correctly and you remember the formula. So just make sure you have that in front of you when you're doing your exam. Maybe just write it down so it's it's kind of easy to compare. Especially maybe after the first term when you compute it, you're like, hey, this is just following a pattern here. So just copy paste. But yeah, if you follow that, then you should get this as your answer. So like before, when we had rules for expected values, we actually have rules for variances as well. And here's the rule right here. If you have a new random variable y, which is again a linear combination of the random variable x, the variance of y is just going to be a squared var x. So this means that, what does this mean? It means that the var, the variance of b, or any constant in that case, it's 0. Okay? This is really important. And if you have an ax right here, the a gets squared. Okay? I guess like one implication of this that you might be interested in knowing is that it doesn't matter if, let's say, your new random variable is like 3x or 3x like this. It's all going to be, the variance is going to be 9 times the variance of the old x. In a sense, you can think of it as if you increase, or maybe if you scale your random variable x, no matter how much you scale it by, if it's negative or positive, your spread will increase. Like it gets more spread out, and that's why you got to square it, okay? So an implication of this is, looping back what I said about independence between random variables, it turns out that if two events, x and y, are independent, then we have the new property here. The variance of x minus y is the same as the variance of x plus y, which is just the sum of the individual variances. So the variance of x plus the variance of y. And this only holds true if it's independent. We won't talk about the case where it's not independent, and I don't think that the course covers that as well. So now that we've talked a little bit about variances, expected values, and we've talked about discrete random variables, now I'm going to introduce to you the most famous type of discrete distribution, the binomial distribution. I think the way I like to remember it is that x follows a binomial distribution if it satisfies the three criteria right here. If I could just write it down. 3 criteria right here. The first one is that it's repeated n times and each trial is independent to each other. This means that the first trial won't affect the second trial won't affect the third trial, and so on and so forth. This means that the trials are independent. Okay, n trials. Oh no. Why is it? Okay, I'm sorry. It just. Okay. N trials right here. So the second. So independent trials. The second condition for x to follow binomial distribution is that each trial can only have two outcomes, which is success and failure. And the last condition for it to be binomial distribution is that each of these trials have the same probability p for success. Now, I think it's not much use for me to just say it, so let's just quickly take a look at an example, yeah? Let's just look at the definition more formally and we'll take a look at an example. So if you already know that x is a binomial distribution, okay, then the probability distribution of x, given again probability distribution, is just this formula here. N choose x, p to the power of x times 1 minus p, n minus x. And if x is a binomial distribution, then we can write it down over here. This is how people like to write down that x is a binomial distribution with n number of trials. So there's this number of trials, and p is the probability of success for each trial. So without much further ado, let's just quickly take a look at how this might apply in a past paper question. So going back to our first question about the flu and the immunization, we already found that the probability that anyone has flu, the probability of flu is 0.25, right? We already found this. So now the question is, what is the probability that exactly 2 out of 4 people contract the flu? So let's say you have any 4 people, what is the probability that 2 of them out of 4 contract the flu? And we can use a binomial distribution like this, right? So I guess the first thing about this is you have to notice that if you have the random variable of, so x being random variable representing number of people flu, then this is gonna be a binomially distributed random variable. Why is this? Look at this. We have n number of trials, n being 4, okay? So n number of 4, and each trial is independent from each other. In other words, one person having flu is independent from the other person having flu, right? So that's why it's independent trials. That's the logic here, independent. So criteria 1 is satisfied. Criteria 2, what's the second criteria? Let me just write that. It has 2 outcomes. So 2 outcomes right here because each person can either have flu or not flu. So that's 2 outcomes, okay? Flu or not flu. Not flu. So 2 outcomes. 2 outcomes. And the third one right here is that the probability of you getting flu is always going to be 0.25. So your P is consistent for all the different trials, so all the different people. Bam. So once you've satisfied these three criteria, then you would know that X follows a binomial distribution. So this makes the question and our lives a lot easier. Yeah. So you would just write out that, hey, X follows a binomial distribution with n equals to 4 and p equals to 0.25. Okay, this is how you characterize it here. And what the question asks us to compute right here is px equals to 2, because it's the number of, so what is the probability that 2 out of 4 people contract the flu? From here, you just need to plug in the formula. Okay, again, we already know what the binomial distribution is. We plug in the formula. Remember, this is the 4 choose 2, so 4 choose 2 times 0.25 being p squared, because, you know, yeah, you just plug in the formula. Maybe I should write down the formula here. So NCR p to the power of r. That's how I write it. 1 minus p to the power of r. N minus r. Your r here is like what is the number of successes you want here. So in this case, your r is equal to 2. So you plug it in. So n is equal to 4. So 4 c. R is equal to 2 since you want 2 successes. P is going to be 0.25. R again is equal to 2 because you want 2 successes. 1 minus p is going to be 1 minus 0.25, which is 0.75. And you have 4 minus 2 here. And you just plug in the formula and you'd get the final probability over here. Yeah? Are we good? Okay. Cool. So with that, there's another slight modification of this question that you might see pop up from time to time. So just now it's asking you to compute like, hey, what's the probability that x is equal to 2? Now it asks you to calculate what is the probability that x is less than or equal to 3. Oh, okay, it looks a lot tougher. Oh my god. Sorry. X is less than or equal to 3. So the idea here is that if you have a binomial distribution and you have this kind of question, technically x less than or equal to 3 is the sum of the probability of x equal to 0, x equals to 1, x equals to 2, and x equals to 3. So those are all the cases in this particular case where x can be less than or equal to 3. Okay? Again, don't always say that it starts from 0 because it depends on what the question asks, right? In this case, it starts from 0 because out of 4 people that have flu, you can have 0 people having flu, right? But it doesn't make sense to say x equals to minus 1. Like this doesn't exist, okay? Yeah, anyways, so you would have the sum of all these different terms here, plus x equals to 4 is equal to 1. Because if you remember, the definition of the probability is that, you know, the sum of all the possible cases is always going to be equal to 1, right? And in this case, because you have 4 different people, you have 5 different possible outcomes here. So the sum of all the possible outcomes will always be equal to 1. So rather than needing to compute x less than or equal to 3 equals the sum of all this individually, what you could do to make your life easier is you just need to take 1, which is the sum of everything happening, minus the probability of x equal to 4. In other words, if I were to translate this into words, the probability of 3 or less people contracting flu is just the probability of not all 4 people contracting flu. Yeah? So it's kind of like the complement there. So, yeah, you just need to plug in the formula again here. So px equals to 4, and you just put in the formula, and boom, you have your answer here. Okay? Are we good? Or any questions? Okay. So one more thing to note about binomial distribution that's important is just the mean and the variance. I think you just need to memorize what the formulas are. Again, based on the characteristics here, if it's b and p, then you just have to find that expected value is just np and the variance is np1 minus p. So that makes life a lot easier. Cool. So at this point, I might ask again, like, are there any questions? All right, great. So we'll continue on now into continuous random variables. So a continuous random variable is the other type of like classification of random variables here. It's slightly different from the discrete random variable because a continuous random variable takes up an interval set of values. Essentially, what it means by interval, it means that, you know, the number of values that this could take is infinitely many. For example, the time it takes for the bus to arrive or the time it takes for the light rail to arrive, right? It could be 5 minutes, it could be 5.1 minutes, it could be 5.6 minutes, you just don't know. It's just an interval of values. You could say it takes between 3 to 4 minutes to arrive, but there's no like discrete discrete value for each one here. In the case of continuous random variables, we have also probability functions. We call them probability density functions. Here. And essentially just it's a curve that describes the random variable under a sample space. And we'll see what the PDF looks like in a little bit here, so don't be boggled too much by the definition. The idea is that the area under the curve, it kind of represents the probability that the events are happening. We have the mean and variance as well for continuous random variable, but this is not accessible, okay? So you're not going to be assessed on this in your assignment or in your finals. Yeah. Before we go into like the whole continuous random variable and an example, I just want to talk about that the expected value rules as well as the variance rules that we learned before, they hold the same for continuous random variables. So it's not any different here. So recall just now that we had that E of y equals to A EX plus B, give in this case here, if they're discrete random variables. Well, it turns out that if x and y are continuous random variables, the same formula holds. So the mu y equals to A times mu x plus B. And the same case holds for variances right here. So if y and x are random variables, then the variance of y equals to the a square of variance of x, given that, y equals to ax plus b. And if x and y are independent, then the variances are just the sum of the individual variances. Okay? Make sense? Yeah? So again, the important thing to note is that these rules that we had about expectations as well as variances, they hold the same regardless whether it's a discrete or a continuous random variable. So don't get confused in your question, in your exam where they might play around, they might give you some continuous random distribution and they ask you to compute the variances or compute the expectations. And I actually have a really good example of this coming up later on. You'll see how these rules might come into play again. So now we look at the most important family of curves in statistics, the normal distribution. Well, everyone talks about it. Yeah? Essentially what it is, it's just a random variable that is characterized with a probability distribution that's a bell-shaped curve. If only I could draw properly. Looks something like that. Oh, it's so ugly. Look, it's just a bell-shaped curve right here. The probability distribution function is characterized by this bell-shaped curve. If it follows a bell-shaped curve, we say that the random variable, is normally distributed, and we write it with this particular formula here. Well, x is normally distributed with a mean of mu and a standard deviation of 1. Oh no, so just standard deviation of sigma. In the special case where x is characterized with a mean of 0 and a standard deviation of 1, we call this a standard normal distribution. And usually we denote this random variable by z. This is essentially really important when you're doing your R stuff, but we'll see how it pans out later on. Okay. So now let's take a look at a question that uses the idea of normal distributions as well as uses the idea of expectations and variances and their rules. So this is from 2021, a very recent exam paper, one of the last questions, and I think maybe one of the more difficult questions in the exam as well. So let's say I decide to create a new random variable, okay, y, from a normal random variable here. This is very important. Normal random variable x. Okay, x follows a normal distribution with mean 5 and standard deviation 2. Andrew then defines y equals to 4x squared minus 29x plus 70. Here. Now, I'm asked to compute what is the expected value of y. So let's just work this out in the whiteboard. Also, one more thing is that there's a big hint that's given here is that the variance of x equals to ex squared here. In this case, just note down this formula, but we'll see how that's used later on. So going back to the whiteboard. Okay, so let's just write down what the question is. We have x. Okay, this is normally distributed by something. Let me see. It's normally distributed with a mean of 5 and a standard deviation of 2. So we write it down like this. Okay. Now, Ry is some really complex looking formula of x. 4x squared minus 29x plus 70. 9x plus 70 here. And we are also given the hit. We are asked to find what the expected value of y is. And note that we are given a hint over here where the variance of x equals to e x squared minus ex squared. Okay, let me just check that that's right. Yep. Right, so how do we do this particular question here? This is where it's very important to remember again that we have tools to help us and we don't need to stress too much about what y is. So let's write it down. The expected value of y is going to be the expected value of this complex looking term here. Okay. Now, it turns out that we can apply the same idea behind the linear expectation of x. The linearity of expectations. But one important thing to note is that when we do this right here, we don't. Okay, hold on. Let me just write it down. So you can apply the same linearity of expectations. So that's the first step in recognizing this question right here. Now, at this point, you might be wondering, what happens to ex squared here? Can we do this? Can we do this? The answer is no. This is not allowed. The reason is because if you square this random variable here, this becomes a new random variable. It's not like the same thing here. This is like, you could call this I don't know, you could call this p, you could call this g, you could call this h or whatever. But the idea is that it's a new random variable, which is why you can't just do this particular expectation right here, where you're just taking the expectation, multiplying it here. That's why we left the term untouched here. But the constants work the same. So if you think of x squared as being a new random variable, you can apply the same rule as before. So you just take the linearity and you just take up the constants here. So that's step one. Now, the step two is figuring out what is ex squared and what is ex. And we'll start with ex first. So let's do ex. So recall that our normal distribution was like this, right? 5 and 2. I think that was what we wrote, right? Yeah, 5 and 2. Now, from our definition of normal distribution and our notation, we have recognized that the mean of x is actually just 5, because that's what the question tells us. This means that we already found that e of x, the expected value of x, equals to 5. So that's solved the first part here. The only hard part left is ex squared. What is ex squared right here? This is where you're not really taught on how to solve for this, which is why they gave you the hint. If you recall, we had that the variance of x equals to ex squared minus ex. Oh, I did zoom up a little bit. Sorry, just let me zoom. Okay, whatever. Ex squared. So this is the term that we're trying to find, right? Which means that our life can just be made easy. You can just like move everything to the other side here. So it's just variance of x plus the square of the expectation of x. Okay, does this step make sense here? Because if you notice from our question and from our formulas, the variance of x is something that we can find, as well as ex here. We already found what ex over here is. We just need to find the variance of x now. Okay? And again, the definition of the variance is that the variance is the square of the standard deviation. So variance of x equals to mu x squared, which is equal to 2 squared, which is equal to 4. Right? Because we were given this in the question just now. Okay? So with this, we already found that the variance of x is 4, and we also know that the expected value of x is 5. So we just need to plug this in. That means the variance ex squared equals to the variance, which is 4, plus 25, the square of 5, 29. So now we have all the pieces of the puzzle. We have what ex squared is, we have what ex is, and the last part is just plugging it back into our formula earlier. Plugging back into this formula earlier, this formula right here. So I just need to plug it back in. So 4 times 29 minus 29 times 5 plus 70. And you would get, was it 41 in the end? Okay, let me just check if I wrote that run. Yeah, 41. So there's your final answer. Okay, I thought this question was pretty tricky. But yeah, just don't fear too much when you're given this kind of question. Remember, again, you have rules to help you out. You don't have to like draw a new distribution or understand anything really. Just make sure to remember that these rules exist, and you can apply them in this sort of manner here. Okay, any questions? Cool. So that was an interesting question from the past, and we're just going to move on really slightly here about normal distributions. So to find the standard normal probability, we use p-norm here. So this is using our output. I just want you guys to remember that what p-norm is, it tells us what this is here. So if you do p-norm c, then it will give you the probability that x is less than or equal to c. X being a standard normal distribution, okay? 0, 1. Oh, should have used Z notation, but yeah. So this is what the p-norm command in R does. It just tells you what the probability of x less than or equal to c is. Less than or equal to or less than, so it doesn't matter here. Less than or equal to or less than is the same thing. So if I were to give you an example, let Z be a standard normal random variable. So Z is characterized by n01. So find the probability that Z is greater than 0.666. So if you remember our probability rule about being complement, yeah, you can apply the same complement rule right here. So essentially, the probability of Z being greater than 0.666 is going to be 1 minus the probability of Z being less than or equal to 0.666. 0.66 right here. And this means you just have to find p-norm of 0.666. Again, an important thing to note is that this only works if your Z is standard normal random variable, and we'll see how to deal with cases where it's not later on. Okay, so just plug it in the formula here and you'd get the answer. Make sense? Makes sense. So let's do another example, this time using Q-norm. Okay, what is Q-norm here? So the idea behind Q-norm, see right here, the idea behind Q-norm is if P-norm C tells us what the probability of C less than C is, then what Q-norm is, it's kind of like the inverse of this right here. So if you do Q-norm Q-norm 0.05 here, right here, this tells us, wait, why am I getting confused right now? Sorry, this is wrong. But yeah, if you have p-norm equals to pz less than c, what the q-norm is, it's just like kind of like the inverse of this particular function. So right here, if pz less than c equals to 0.05, this means that c, this middle term here, is equals to q-norm 0.05. So you just reverse it really. If I give you another example right here, if like pz less than d equals to a, right? We have like two different terms here. This means that q norm a equals to d. Hope that's not too confusing. So this is pretty useful in some cases because they like when within exam questions they like to mix between the two using p norm and q norm, and it will come in handy when you're dealing with some of the exam questions. So we'll take a look later on as well. But let's just briefly move on from now, and we'll talk about the probability of intervals right here. So just now we already found using p-norm we can find z less than c, right? But what happens if you have something like this? Well, essentially, if you have a less than z less than b, you just have to break it up apart. And the rationale is because if you draw the random normal distribution, okay, let's say this is b, this is a, the probability of z being less than these two, it's just this shaded area down here. So if I'm going to draw it again, if I'm just going to draw this right here, let's say you have this nice little normal distribution right here. If you want to find z less than a, less than b, what you would need to find is you would need to find this area right here. Okay, you need to find this area in the middle, right? Well, you can find this area in the middle by getting the first area, which is the area of b, of z being less than b, so this area here, and you find the second area, which is z less than a. Excuse my drawing. So this is going to be z less than b, z less than a. And if you notice, the difference between these two, z being less than b and z less than a, it's the middle shaded area here. So that's how you remember that, you know, if you're doing with intervals, it's just the difference between the two p norms here. So this would be p norm b, and this would be p norm a. Okay, does that make sense? So going back to our lecture example. So an example here is like this right here, minus 1.26 and 1.6, and it's just 1.6 minus 1.26 using the p norms right here. Yeah, I think I would recommend, if you're gonna do this kind of question, just try to graph it out, and you would be able to see like what you're trying to solve for. And one more thing that's important about normal distribution is that it's symmetric. This means that if you're looking over the normal distribution again and you have c here and minus c, then these tail probabilities, they're the same. So let's see how we might apply that. Right here. Compute the probability that p of z is greater than minus 2 and less than 2. Why are people outside? Okay. I thought they might want to use the lecture theater. Okay, anyways, of z being less than 2 and greater than minus 2. So, what we want to do now is we just want to take the distribution right here. Okay, sorry for that. Not so sure what's happening in the back there. Okay, so we just want to take this probability right here, and this is symmetric right here. So this area right here is the same as this area here, and we are given that p norm of 2 is so z less than 2 equals to this particular thing right here. Okay, now what you can do with this is, if you note this, if you find the complement of this, which is going to be z less than 2, this is going to be probability of z greater than or equal to 2, right? So essentially, if you take 1 minus this probability here, you would get the tail probability of this one right here. Okay, so if you already have the tail probability and you're asked to find something, you have the tail probability, then you would notice that that means the total shaded area here is going to be 2 times the tail probability. And once you have that shaded area that's over here and over here, you can easily find the middle shaded area by taking the by subtracting that. So kind of see how it goes up here. Right here. I'm not a fan of the algebraic way, so let me just rewrite that in terms of the whiteboard. I'm going a little bit over time here, but let me just quickly show you guys that. Oops. Yeah. So there's going to be 2. It's going to be minus 2. We want to find the shaded area here. So what we'll do is we find this area. We take the sum of this area here and this area here, and then we do 1 minus that sum right here to get this middle area. Does that make sense? Yeah? Cool. So, yeah, I guess the last part here to end off the normal distribution part is on standardization. The idea is that if you have a non-standard normal distribution, you know, given mean, mu, and standard deviation of sigma, then you can standardize z by simply subtracting by mu and dividing by sigma. Okay? And you would get back the standard normal distribution right here. Now recall that I said that if you want to use P norm and Q norm, you can only use it if you're dealing with standard normal distributions, right? So if you are faced with a distribution that is not standard, you have to standardize it first before you can use P norm and Q norm. So let's just see how we might apply that in an exam question. So there's a tricky question right here. Suppose that X is normally distributed with -3, 4, and that Z follows the standard normal distribution. Suppose that Px less than X equals to 0.4. Now compute the value of X such that Px less than X is equal to 0.4. So I'll just try to write that down. So we are given that, I'll do this really quickly. We are given that X is normally distributed like this. Oh, -3. Yes, normally distributed here. And we want to find probability of X less than X equal to 4. Is that it? 0.4. 0.4. So the first thing to note is that if we have something like this, I think we should standardize this first so we can make use of our P norm and Q norm, because what we're trying to find is this variable right here. So let's standardize it first, okay? So let's define Z equals to X minus -3 divided by 4. So this is going to be X plus 3 over 4. And this is going to be normally distributed, standardized. Okay? So this means that the probability of Z being less than small x plus 3 over 4, this is also still going to be 0.4 right here. Okay? Now, one thing to note is that if you standardize the random variable, you have to standardize the observed value as well, which is why whatever happens to your Z here, your X, has to happen to the small x as well. Yeah? And you would get 0.4 here. And then remember what our function Q norm, this is where it comes in handy, because our Q norm exactly helps us to find this. So we can now write that Q norm 0.4 equals to X plus 3 over 4. Because that's what the Q norm does, right? And finally, you just have to manipulate it to make X on the small side. So 4 times Q norm 0.4 minus 3. And that's your solution here, if you want to find the observed value of X. Okay? Does that make sense? Cool. I think that's pretty much it for my part here. I will probably pass it on to Gerald if there are any questions, but I might ask again, like, do you guys have any questions about probability, random variables? No? Right, all good. So I'll pass it on to Gerald then to take it on for the next half of the course. Okay.
We'll probably take a 10-minute break and then we'll resume at around 2:30.
Did you see there were a bunch of lecturers outside? 3 of them just staring inside. I was like, what is happening? Because I was like, wait, are you going to tell us to get off or? Yeah, you did. Unless I fucked up and saw it wrong. But I based it off, like, MathSoc defense. It shouldn't be wrong. CO4. Have to leave at like a bit early. Maybe I'll leave like 3. Get some food first before the next one. Alright, okay. Let's quickly take a picture. I'll recognize it. Okay, open. So much trouble with the phone because it was really wrong. It takes a bit of time to use. Yeah, that's right. I was like, I couldn't write as much as I'd like to on the slides. What time is 3 next week? Tuesday, Thursday. Thursday was 5. So the day before. Oh, the day before the actual 371. That's good. That's fine. Yeah. That's fine. Thank you. We need to find like any of the stream by the way. Because like I think the stream is up to 1. I don't know if it's a 1. It's fine. It automatically cuts off there. I want to finish it. I told the guys, like, hey, you might want to rethink our approaches if like the number of things coming graded for some courses. Because like it's a lot of effort and it feels bad for people as well. Just to 1A, 1A, 1A together. It was pretty hard because we were working on the availabilities of our supplementers as well as the timings of the classes, and it turns out that 101 and 102 classes are quite close together. And like all of the slots that they could do are subcom could only do today. Not today, it was yesterday. So it ended up that way. It was kind of unfortunate story. So we could do something with that. So that's the thing, like we did ask them, but we tried not to do something with them because we assumed most people wouldn't want to come to campus anymore. Yeah. It's like, we 10 people to go for classes, and then like broke over after your classes. But it turns out people can't. People are tired to do 2 seminars, one after the other. By the way, your battery's like advertised.
we might just get started a bit earlier. So welcome to the second part of the seminar. We're going to be going through statistical inference. So in the first part, we basically looked at different types of data and like what sort of things, what sort of data that we might expect. In this topic, we're going to be mainly concerned with what we can do with data. And then we can make statistical inferences out of the data that we have. So remember that in the previous part, we basically looked at random variables. And remember that we can look at a new random variable. So if we define ax plus by to be a whole new random variable, what we can do is we can also compute the mean and the variance. So remember that the variance, if you want this sort of formula, you require independence. Whereas if you have the linear combination of means, then you don't need the independence. So this is going to become important because when we're talking about a random sample, these sort of properties are ideal for us. So for a collection of random variables to be a random sample, we require two things to occur. So the first one is that we want it to be independent, and then we want it to be identically distributed. So for the first part, we ideally want independence because we want to deal with these sort of things here, where it's easy to deal with these the variances. So we can just sort of split up the variances accordingly. The second thing is identically distributed. So this just means that they have the same mean and they have the same variance. And if you have both of them together, we call them IID. So IID stands for independent and identically distributed. And if you have a bunch of random variables, so if you have just x1, x2, up to xn, if they are IID, then we call them a random sample. So IID, then we call it a random sample. Does that make sense so far? Cool. Okay. Alright, so the first thing is, so we basically just define what a random sample is. So a random sample is just a collection of random variables that are identically distributed and are independent of one another. So that's all you need to know. And the good thing about these sort of properties is that it's really easy to deal with the mean and it's easy to deal with the variance. And consequently, it's easy to deal with the standard deviation as well. Okay. So let's have a look at the sample mean. The sample mean is probably the most simple random sample that we can consider. So what it basically is you basically sum up all of the random variables and you divide by the number of samples that you have. So for example, if you had something like x1, x2, x3, and x4, then the sample mean is just going to be x1 plus x2 plus x3 plus x4 divided by 4. So you're just adding up all of the random variables and then you're just dividing by the number of samples. Now this is really useful, right? Because we have a lot of things to work with here. So one thing you can note is that the mean of the new random variable is precisely the mean of any one of these random variables because each of them are identically distributed, so the mean across all of these random variables are the same. And you can verify this, so this is very easy to check, right? Because if you consider the mean, so if you consider the expectation of y, so that's just going to be the expectation of this entire thing here, divided by n, And then we can abuse the linearity, so we can bring the 1 over n to the front. So that's going to be 1 over n times the expectation of this part here. And because remember that each of them are identically distributed, what we end up having is that we have n divided by n times the expectation of any one of these. I'll call it x. And so we have the expectation of x. And that's precisely what we have here. And likewise, you can sort of do a similar process with the variance. And as a result, you can also do the same thing with the standard deviation. Okay. So this is really nice because these are really neat formulas that you can sort of just remember. But these occur because you have x1, x2, xn being a random sample, and then you're considering the sample mean. You have to do a bit more work if it wasn't the sample mean, but the derivation would be more or less the same. Okay, so one thing that we wanted to know from the previous part is that we relied on two things for this to work. So we relied on the fact that we knew what the mean was, and we knew what the variance was, or we knew what the standard deviation was. But in the real world, you'll most likely have either none of these information, or you'll have one of the information. And most likely you'll only receive the mean, and you don't know anything about the spread. So what we can do instead is we can sort of estimate this spread here. And instead of just looking at the mean, we can just try to estimate how good the spread is. So there are different ways to estimate it. So the first way is to construct a confidence interval. So intuitively what a confidence interval is, it's the probability. So it's an interval, right? So what we can do is it's just going to be an interval where we are X% confident that the true value lies inside. So if I have an interval, I don't know, let's just say X to Y, then the confidence interval is going to tell us exactly how confident we are that the true mean or the true value will lie inside this interval here. Does that make sense? Cool. So this is one way to estimate an unknown parameter. So we can instead construct intervals that tell us with a lot of confidence whether the true value is inside the interval. So there are sort of two ways of doing this. So the first way is more or less an estimation or an approximation. So this one relies on the fact that, roughly speaking, we know that 68% of data is within one standard deviation away from the mean. 95% of data will lie roughly about 2 standard deviations from the mean, and 99.7% of data will lie within 3 standard deviations from the mean. And so this is a very rough, but it's a fairly good estimation for the actual confidence interval. And then the other one is, instead of estimating, we can actually get a precise confidence interval depending on the level of confidence that we're after. So let's have a look at the first method. So the 68, 95, 99.7 rule basically just says that 68% of data is within 1 standard deviation, 95% of data is within 2 standard deviations, and 99.7% of data is within 3 standard deviations. So if I consider a normal distribution, and I consider some mean, so this is just going to be the mean, then if I consider all of the points inside 1 standard deviation, we're going to have roughly 68% of data inside here. Similarly, you know that roughly 95% will lie in here, And then lastly, you know that, let's just put it in purple, 99.7% will lie inside this region here. So that would be 99.7%. And so this is actually, it will give you a good estimation for like how confident we are with where the true mean is going to lie. But again, this is just an approximation. It's not an exact or precise confidence interval. So let's have a look at an example which comes from a midterm, and you probably have seen this question or something similar to it as well. So we're going to be considering data sampled from student IQ scores, and we know that they are approximately normally distributed with a mean of 96. So let's highlight that. So we have a mean of 96 and a standard deviation of 6. So the first question asks us for the proportion of student IQ scores that are between 84 and 108. So let's take both of these pieces of information and let's see what we can do here. So first things first is we know the mean is 96 and we know the standard deviation is 6. And we are asked to find the proportion of student IQ scores that are between 84 and 108. So proportion of scores that are between 84 and 108. So the first thing you can kind of see is, well, how far away is 84 from our mean? If you do the math here, you should get that it's 12 points away from the mean, right? So you have 96 minus 84, that's equal to 12. And similarly, you know that 96 plus 12 is 108. So what does this tell you? Well, it tells you that this is actually 2 standard deviations from the mean, and this is also 2 standard deviations from the mean as well, right? Because the standard deviation is 6, and you are 12 points away from it. So by the 68, 95, 99.7 rule, what that tells you is that if you look at this graph, or if you look at your normal distribution, then we're basically finding all of the scores that lie within 2 standard deviations. Roughly how many, what proportion would lie inside this region here? It would be 95, right? 95% of data will lie inside 2 standard deviations from the mean. Right? So for the first question, it's roughly 95%. Cool. All right. Does that make sense? Cool. Okay. So we've just finished question 1. So I'll just highlight that. Okay, so question 2 asks us, what range contains the central 68% of IQ scores? So for this question, we want to basically find the confidence interval where we have roughly about 68% confidence. So here, remember that 68% of data is within 1 standard deviation. And so an easy way to construct this is, well, remember that the mean is, so remember that the mean here was 96 and the standard deviation was 6, right? So if you're within 1 standard deviation from the mean, then you need to be 96 minus 1 times 6, and you need to be 96 plus 1 times 6. And if you compute this interval, what we get here is 90 and 102. Yep. So this is going to be the confidence interval for 68% of data. Cool. So let's just highlight this. All right, so for question 3, we have that Ella has an IQ of 114 how many standard deviations above the mean is Ella's IQ? Okay, so remember that our mean is 96, standard deviation is 6, and we know Ella's score is 114. So let's see how far away Ella's score is from the mean. So we know that Ella's score was 114. We know the mean is 96, and we know the standard deviation is 6. So if we do the math here, this is going to be roughly, I think, 18, right? So this is going to be 3 times 6, which is 3 standard deviations. So for Ella's score, Ella's score is 3 standard deviations above the mean. Cool. And then last question. So this one is probably the harder question. So all of the other 3 questions should be fairly straightforward. So we basically want to find the proportion of students in the school that have an IQ higher than Ella's IQ. So let's think about this. So in the previous question, we noticed that Ella's score was 3 standard deviations above the mean. So what you can do here is you can kind of draw it up. Oh my god, that's so bad. And we can see that this is Ella's score. So this is 114, this is 96, and we are 3 standard deviations above the mean. We want to find the proportion of students who scored higher or who have an IQ score higher than Ella's score. In other words, what we're basically trying to find is this proportion here. Well, remember that what we know is because Ella's score is 3 standard deviations above the mean, we know that 95% of scores will lie in this region here. So this is going to be 95%. But the issue is that we also need to account for this small region here, right? And this small region is actually precisely equal to the one that we want to find, because we have a symmetry that happens on the tails. So instead of finding this proportion here, we can actually just find this proportion here. Or we can find both of these proportions here, and we can just divide by 2, because both of them are going to be identical. So remember that the area underneath the normal distribution is going to be 1, right? So that means the sum of the tails have to be 5%. So we note that this is going to be 2.5%, and this is also going to be 2.5%. Yeah? Oh, yeah, sorry. It's 99.7. My bad. We are 3 standard deviations, not 2. Okay, yeah. So this is 99.7%. So the sum of these are going to be 0.3%. Right? So this is going to be 0.3 divided by 2, which is 0.15. Oh no, that's wrong. It should be 0.03, which is 0.015. And then so you have roughly 1.5% of people are going to lie above the score. Does that make sense? Yeah, cool. Does anyone have any questions? No? Okay. Cool. Alright, so we can move on then. So that whole idea was trying to estimate what proportion of data lies within standard deviations. But the number of standard deviations is just an approximation. What we're going to do is we're going to go for an exact value instead. So what we're going to do is instead of looking at the number of standard deviations, we're actually going to be using exact quantiles instead. But everything else pretty much remains the same. So the only difference, the only real difference here is that instead of using the number of standard deviations, we're going to be using exact quantiles instead. And so this is what the Z star here does for you. So the Z star here is going to be the value such that the probability that you lie within Z star is going to be the exact level of confidence that you want. And so what you can do here is remember that you're taking samples, so you're not taking infinitely many random variables. And instead what you can do is you can actually use the sample standard deviation, right? So another way of looking at this is that this is your mean. So this is the mean of your sample. This is your sample standard deviation. And then you're looking at this as your exact quantile. So exact quantile. So the whole process actually works pretty much the same way as we would expect with your 68, 95, 99.7 rule, except instead of using approximations, we're going to be using exact values. And then as a result, you end up getting this confidence interval here. So another way of looking at it is that you're looking at, let me just write it up here. So you're looking at mean plus or minus Z star times standard deviation. Cool. If you don't know what your actual standard deviation is, instead you can approximate it using what we call a t-distribution. So instead of calculating the exact value using the normal distribution, we can just replace everything with a t-distribution instead. So have a look at this. So instead of working with Z star, which comes from your normal distribution, you can instead replace it with T star, where T star here is a value computed such that you have this result here. So it's exactly the same, except you're replacing the normal distribution with a t-distribution, which for large enough samples is a good approximation for your normal distribution. And remember that we no longer have the true standard deviation, so that's no longer given to us. So instead of using the true standard deviation, what we can do is we can replace it with what we call a sample standard deviation. And the sample standard deviation is just this formula here. So it looks very similar to a standard deviation, except you have one less degree of freedom here. So instead of dividing by n, you're actually dividing by n minus 1 here. But everything else works exactly the same. So you can see that we still have the mean here because we know what the mean is. We instead of the Z star, which comes from the normal distribution, we have a t distribution, and then we just replace our true standard deviation with our sample standard deviation. But everything else works in pretty much the same way. Yep. Does anyone have any questions? No? Okay. So this is useful because it tells us a lot about like roughly where the location of your true mean is going to lie. But the idea is that we want to try to reduce the confidence interval, right? Because if we have a really large confidence interval, it doesn't really tell us a lot. This is where we can kind of use our claims, we can kind of prove or disprove claims using what we call a hypothesis test. So the general setup with a hypothesis test is that you have roughly one claim that you want to prove or disprove, and then you have a claim that's sort of the best at the moment. And what you want to do is you want to pit them against each other and see who wins. So this is what we call the null hypothesis, and this is what we call the alternative hypothesis. And these two are going to be the contestants, and we're going to see who wins by using all of these evidence. So after stating your null and alternative hypothesis, what we want to do is we want to come up with a test statistic, and we want to compute the value of it, given that the null hypothesis holds. And then from there, we want to compute the p-value, which tells us roughly what conclusion we should make. So it tells us how good of an evidence we have for the alternative hypothesis and against the null hypothesis. So remember that we want to try to prove the alternative hypothesis, which means that we want to reject the null hypothesis here. So for the first part here, it's usually a fairly straightforward step here. So you want to just figure out what your null and alternative hypotheses are, and then you want to just claim them, essentially. So there's nothing else to do. You just have to figure out what the hypotheses are that you want to test, and then you pit them against each other. So the notation here for this course is H0 usually means null hypothesis, and HA stands for the alternative hypothesis. So the second part is to compute your test statistic. So the test statistic comes in many forms. So the two that we've basically looked at so far are the normal distribution and the t-distribution. And these two, you basically use them depending on the situation you have here. So if you know what the standard deviation is here, you use the normal 0-1 distribution. So you use the standard normal distribution. But if you don't know what your standard deviation is, you can approximate that using a sample standard deviation instead. And as a result, you end up with using a t-distribution. So we'll have a look at an example a bit later on, just after this. So we're going to basically use the test statistic to then come up with a p-value. And in MATH1041, we typically just use this table here to figure out how strong of an evidence that is. So the smaller the p-value, typically the stronger the evidence against the null hypothesis is. Right, so you can see that here, 0 up to 0.1%, it means it's very strong evidence, and which means that we typically want to reject the null hypothesis. Between 0.1 and 1%, we still typically reject the null hypothesis. There's still enough evidence to say that, it's more the alternative hypothesis is probably the more favorable model rather than the null hypothesis. But once we get up to something like moderate evidence, weak evidence, and little to no evidence, it's hard to say. And because it's hard to say, we don't necessarily reject the null hypothesis, but rather we just say there's not enough evidence to reject the null hypothesis. Does that make sense? Yeah. Cool. All right, so let's have a look at an example to try to clarify what it all means. So we have that a gardener needs to determine the pH of the soil in her garden, and she will add lime to the soil if the pH is less than 6.5. So remember that she will add lime to the soil if the pH is less than 6.5. So that's something to keep in mind. She takes 16 samples. So these are not your true... So these are samples, right? So you don't have a true standard deviation, but rather the standard deviation that you get comes directly from a sample, and as a result, you have what we call a sample standard deviation. So even though the question doesn't specify it's a sample standard deviation, you should be able to infer that because we are coming from a sample, the standard deviation that you get is indeed a sample standard deviation. And we want to carry out a hypothesis test to determine whether the gardener must add lime to the soil. So what do you think the null hypothesis is, and what do you think the alternative hypothesis will be? So here, remember that we are trying to determine whether the gardener must add lime to the soil. So we want to find evidence that she will add lime to the soil, meaning that the pH is less than 6.5. So we want the mean pH to be less than 6.5. And if we can find evidence for this, then we will determine that she will add lime to the soil. And as a result, the null hypothesis is going to be the pH is, or the average pH is 6.5. So something to keep in mind, this is what we call a one-sided test. You can certainly have a two-tailed test, and you can also have a one-sided test as well. And so what that means is that you have to be careful when you're computing your p-value, because you're only caring about what happens at one of the extreme ends. You don't care about what happens on both extreme ends. If you had what we call a two-tailed test or a two-sided test, then you would have to worry about both of the ends. But because we have a one-sided test here, we only need to worry about what happens at this end here. Yeah, cool. So the first step is to state the null and alternative hypothesis. So that's what we did here. So we said that the null hypothesis was that the pH was equal to 6.5, and the alternative hypothesis was that the pH was less than 6.5. The second step is to compute the value of your test statistic. So to do this, we need to come up with a distribution that we're going to be using. Well, the good thing is that we know that it comes from a sample, so which means that we don't have a true standard deviation, but rather we have a sample standard deviation. So the test statistic that we're going to use, or the distribution of the test statistic, is going to be a t-distribution. Now the question is, how many degrees of freedom should we have here? And the degree of freedom that we're going to have is always one less than the number of samples that we have here. So in this case, we had 16 samples. So the distribution of your test statistic is going to be 16 minus 1, which is t15. So we're going to have a distribution which is t-distributed, and it's going to have 15 degrees of freedom. Cool. And so what we can do is we can just compute this here. So remember that our test statistic always comes in this form. So it's always going to come in this form here, where you have the mean minus the value that we want to test. So here, here this is what we call an observed mean. Here, this is going to be the value we want to test. And then the bottom is going to be the standard deviation that we have. So if we plug everything in, so the observed mean that we had was 6.3. So you could find this by going back to the question. So remember that she observed an average pH of 6.3. So that's going to be the observed mean that we want to use, minus the value we want to test, divided by the standard deviation here. And then all of these values we already know. So we can just plug everything in, and then we get this value here, which is minus 2.67. Does that make sense? Cool. So the last step we kind of want to do is we need to compute the probability. So we want to compute the probability that you observe a value that's more extreme than the value that we examined here. So your p-value is going to basically determine what the probability is that any observed value is less than 2.67. And so what we can say is that if the probability is really, really small, that means minus 2.67 is probably more extreme than any other observations that we can make. and therefore we can say that this number here is less likely to happen, and so we can reject it. And that's the whole idea why we reject it for smaller and smaller p-values. So the last step is really just to find the null distribution, which is just a t16 minus 1 or a t15 distribution. And then we just compute the p-value. So here we are basically just computing the probability that t is less than minus 2.67. If you had a two-tailed test instead, so if you had a two-tailed test, what you're basically looking at is all of this portion here and all of this portion here. And so you need to compute each of them separately. But luckily for us, we only need to deal with one side here because we only have a one-tailed test. And so you can compute this using R. So yes, let me boot up R and I'll show you how you can compute this if you needed to compute it. Don't worry about this. So inside your terminal, what you can do is you effectively want to compute the probability, right? So you compute the probability of a t-distribution. And so what you can do is, in R, P is always to compute the probability. And then you have something here, which will stand for what the distribution here is. In this case, because it's a t-distribution, you want to use PT. So to do this, what we can do is PT, and then we have different parameters that we can pass in. The first parameter is going to be the quantile that you want to consider. So in this case, it's going to be whatever value here is. So it's going to be whatever this value here is. So what we can do is we can go minus 2.67. And with a t-distribution, we always need to declare how many degrees of freedom our t-distribution is going to take. So we can do this by specifying df, which is degrees of freedom. And then what we can do is we can just say 15. And this will tell you a probability here. And so this probability here is precisely your p-value. And you can see that it's roughly, 0.8%. And so you're more likely to reject it rather than not reject it. So once you have that computed, you basically just conclude. And there is strong evidence to reject the null hypothesis, and therefore we conclude that the gardener should add more lime to the soil. Does that make sense? Yeah. So this process is more or less the same every time. So the hardest part of a hypothesis test is really to figure out what test statistic that you want to use. And this comes from the question itself. So the question will try to hint towards specific kinds of test statistics to use. And it also depends on what sort of data you also have, and whether we have a true standard deviation or we have a sample standard deviation. Cool. So the last part of this section here is to just briefly talk about the central limit theorem. So the central limit theorem is a really powerful theorem here, because what it tells you is that if you sample for large enough, so if you sample for long enough, it doesn't matter what distribution your original random variables are. The sample mean is always going to approximate a really nice normal distribution. So if I have x1, x2 up to xn, then as we sample more and more random variables, this will approximately follow a normal distribution with mean mu and standard deviation being this. But there are assumptions that we have to make here for this to work. So the first thing is that each of these random variables have to be independent and identically distributed. In other words, what we can say is that these actually form what we call a random sample. So remember that a random sample is just a collection of random variables that are IID. So here they form a random sample. And the second assumption we want to make is that the sample size n is sufficiently large. Whatever that means is up for debate, but generally speaking, as you sample more and more random variables, so as you sample more and more data, then you'll eventually get what we expected, which is a bell curve or a normal distribution. Cool. And so this is precisely why the central limit theorem is so powerful, right? Because we can sample from, say, a binomial distribution, or we can sample from a geometric distribution, exponential, but no matter what distribution we take, the sample mean will always approach a normal distribution. Cool. So let's have a look at this example, which comes from a 2018 paper. So it's been a while since this question popped up, but we're going to be using the central limit theorem with the 68, 95, 99.7 rule. And we want to answer these questions here. So the first question is, we want to compute the probability that the average weight of the 16 women is more than 74 kilos. And we are given some assumptions, or we're given some assumptions about the distribution of the weights of the women. So by the central limit theorem, remember that if you sample for a lot large enough, the sample mean will approximate a normal distribution. And we have precise means and standard deviations. So if we just plug everything in, so we already know what the mean is, we already know what the standard deviation is, we know how many people we sampled. If you plug everything in, then we should get that x bar, so the sample mean, follows a normal distribution with mean 72 and standard deviation 2. So the second part is we want to compute this probability being greater than 74, because that's what the question asked us. So by the 68, 95, 99.7 rule, notice that 74 is one standard deviation above the mean. And so what that means is that we can verify that the probability that x bar being greater than 74 is 0.16. So here's a way to kind of justify this. So let's have a look at, so we have a normal distribution, and it's centered around 72. We want to basically find the probability that this portion, we basically want to find the probability of this portion here. But remember that this proportion here is roughly 68% of all data. So that means on both ends, so this end and this end, they both sum up to 32%. And because we have a symmetry happening here, we know that each of these ends are going to be 16% each. And so therefore, one tail would be precisely 16%. Cool. Right. And so that's how we can justify that the probability is 16%. So the second part asks us to compute the probability that the total weight is more than 1,184 kilos. So the total weight is going to be the sum of all of the random variables here. So the total weight is going to be something like, you can't see that. So it's going to be x1 plus x2 plus x3 up to x16. And we want to find the probability that this total weight here is more than 1,184 kilos. So what we can do here is the following. Okay. So remember that the sample mean is actually just the average among all of the random variables, right? So what we can say is that we can manipulate this expression here to get that x1 plus x2 plus up to x16 is precisely equal to 16 times the sample mean. And so solving this probability is equivalent to solving an easier probability here. And what we can do is we can just divide by 16 and we get that the probability x bar is greater than 74. But remember that this is actually what we've already solved in the previous part. So both of the probabilities are exactly the same. And therefore, the probability is also 16%. Does anyone have any questions about it? No? Okay. If you have any questions, feel free to also ask any time as well. Okay, so that basically ends the 5th chapter. I'm going to spend a little bit of time on chapter 6, and then basically the rest of the seminar is going to be a rehash of what we've already done, but we're just going to be doing it for 2 parameters instead. So it's more or less the same thing as what we've done, but we're just adding in an extra layer of difficulty by adding in another parameter. So the first thing we kind of want to talk about is a sample proportion. So remember that in the previous part, we've talked about a sample mean. Well, this time we're going to be talking about a sample proportion. So we're going to assume a binomial distribution. So a binomial distribution takes in 2 parameters. It's going to take in the number of trials. It's also going to take in a probability for each trial. Then we can estimate the probability. So if we don't know what the proportion is, then we can estimate it by using a sample. And it turns out that the estimation for the probability is precisely equal to x divided by the number of trials. And this is what we call the sample proportion random variable here. So p hat takes in a random variable, is a random variable. And it also describes the sample proportion given n trials. And it turns out that what we can do as well is we can find the mean and we can find the standard deviation as well. So you don't need to know how to derive these. You just need to memorize each of these components here. And then it turns out that if we just take the square root, we evaluate the standard error, which is also, so the standard error is going to be the standard deviation evaluated at p hat, because p hat is an estimation for p. And so what we get here is that it's going to be p hat times 1 minus p hat divided by n. The actual standard deviation, though, is going to be the square root of p times 1 minus p divided by n. But it's just that we don't know what p is, right? So we can't really evaluate the standard deviation unless we know p. And therefore, what we can do is we can just take a sample instead, and we can just estimate p with p hat, and we get what we call a standard error. Cool. All right. So the good thing about a binomial distribution is that, again, if we sample for large enough, we can actually approximate it using a normal distribution. And it turns out that the normal distribution will have the same mean and the same variance. So if you take x to be approximately normally distributed, which is with parameters np and the square root of np times 1 minus p, then p hat, when we estimate it, is also going to be normally distributed with mean p and pretty much the same standard deviation. So that's actually really convenient for us because we can actually switch between a normal distribution, which is a continuous random variable, and a binomial distribution, which is discrete. So we can switch between the two for fairly large values of n. And here we have to make the assumption that n is large enough such that np is greater than or equal to 10, and np times 1 minus p is also greater than or equal to 10. And if both of these hold, then we can use the normal approximation to deal with a binomial distribution. Cool. So all of this actually comes from the central limit theorem, and it's the reason why we can actually approximate it using a normal distribution. But there's a problem here, because we are going from we're going from a discrete random variable to a continuous random variable. And so they take in very different values here. So what we can do is we can actually correct this by introducing what we call a continuity correction. And the idea here is that instead of looking at the probability that x, say, is less than or equal to 5, this is also equivalent to saying x is less than, say, 4.5. Or actually, should be 5.5. Yeah. And the idea here is that for a binomial distribution, you want to include this x equals to 5 part. But if you include it in a normal distribution, so if you only consider x equals to 5 for a normal distribution, you get a probability of 0, right? Because the area underneath the curve at exactly one point is 0. So what we can do is we can actually make for the correction by introducing a continuity correction here. And it's really just to subtract or add 0.5 depending on what you're trying to do here. So for example, if you have p being x less than 5, what you can do is you can approximate it by the normal as the probability that x is less than 4.5, because you don't want to include the 5 as well. So actually you don't even care about what happens at 5. And so what you can do is you can subtract a 0.5 and you still don't change the probability. And similarly, if you want to include the 5, then you add 0.5, because you also want to account for the fact that x could take on 5. Does that make sense? Yep. So there are formulas for this, but it's the easiest way to think about it is to try to logically think about what happens if you take on the endpoints. So if you want to take on, if you want x to take on 5, then you want to also include 5 when you're approximating using the normal distribution. Cool. So in doing that, what we can do is we can also compute the confidence interval for proportions. So remember that we can standardize your proportion here. So remember that P here follows a binomial distribution with mean P and with standard deviation P times 1 minus P divided by N. And so what we can do is similar to how we we standardized from before. What we can do is we can also do the same thing here. So remember that we can also approximate this using exactly the same parameters, but instead of using a binomial distribution, we can also look at a normal distribution as well. And so what we can do here is we can standardize this. So to standardize, we subtract the mean. So we subtract the mean, we get this part here, and we divide by the standard deviation. And so that's why we get this. So that's why we get this part here. And because we've standardized it, this actually follows a normal distribution. And it follows a standard normal distribution, in fact. Okay. And, the confidence interval is exactly the same. Here you get the standard deviation. So here you get the standard deviation, So it's basically the mean minus the exact quantile times the standard deviation. And then you do the mean plus the exact quantile times the standard deviation. So it's exactly the same as what we did before. Nothing ever changed. The only difference is that we're looking at proportions instead of means. So let's have a look at this question here. So we want to basically derive the 95% confidence interval for this true proportion here. So if we want to assume this following result here, what we can do is from before, we can just standardize this so that it becomes a normal distribution. And so that's what we had here. So once we standardize it, we get a standard normal distribution. And then to construct a 95% confidence interval, you basically want to look at, well, we want to find the probability that this proportion here lies between 2.5 and 97.5% percentiles. And I'll let you think about why we're looking at 2.5 and 97.5%. But in that case, we can basically get this result here. So we basically want to find the z star such that this proportion here lies between minus z star and z star. And that's exactly how we found z star as well. And so what we get here is that because this probability is equal to 0.95, the confidence interval becomes what we have here. Does this make sense? So you can solve for p. So remember that what we're trying to do is we're trying to solve for p here. So we can just multiply by the standard deviation, and we can subtract p hat, and then we can just divide everything by -1. Cool. And if you do the math, you end up with this. Cool. And then question 2, it asks us to construct a 95% confidence interval for this question here. So the proportion here is 466 divided by the total, which is 6,272. So P is going to be, or P hat here is going to be 466 divided by 6,272, and N is going to be 6,272. And once you get that, then you've basically got your confidence interval here. Does this make sense? Cool. All right. We're going to have a look at another example as well. So here we have a newspaper. A newspaper reported news poll results where voters were polled on their preference between the two major Australian political parties, the Labor and the Liberal. The proportion preferring Labor was 0.51. Suppose that the news poll sample size was n equals to 100. So we have a sample of 100 people. Making the necessary assumptions about the sampling process, construct a 95% confidence interval for the proportion of Australian voters preferencing Labor at the time of the poll. And we're also given these RStudio output as well. So we don't have to use R ourselves. Okay. So the first thing we kind of want to notice is that the proportion preferring Labor is 0.51. So because we want to construct a 95% confidence interval for the proportion of Australian voters preferencing Labor, the proportion estimation is going to be 0.51. So that's the first observation that we can make. And so because we found what p hat was, we can also find what the standard error is. So the standard error is always given by this formula here, and that's equal to 0.05 once you plug everything in, right? So you get the square root of 0.51 times 0.49, because it's 1 minus 0.51, all over 100. And so if you do the math, you end up getting something like 0.05. So the 95% confidence interval is given by this. So you just plug everything into your confidence interval, and then you get the result here. Does that make sense? Cool. So the last part of this, the last topic of this part here is just hypothesis testing. So it's more or less the same as what we've done before, but this time we're just branching away from looking at means to looking at proportions. But effectively, it's all going to be the same. So in the usual case, we have that the hypothesis, that the null hypothesis is going to be that the probability, the true probability is equal to P0, so whatever P0 is going to be. And then the sampling distribution is going to be something like a normal distribution. So under the null hypothesis, we are going to be using a standard normal distribution here. Cool. And that's effectively it, because all of the process is exactly the same. It's just that you have different hypotheses that you want to test. Cool. Does anyone have any questions before we begin the last part? No? Okay. So the next part is we're going to be doing statistical inferences again, but instead of looking at one parameter, we're going to be looking at two parameters. But it's more or less going to be the same process anyway, so I'm just going to kind of brief over it, but you're just going to be introduced to some more types of distributions, and then we're going to be looking at how you can identify one from the other. So the first one we're going to be looking at is what we call a two-sample t-test. So one of the assumptions that we're going to make here in order to use the two-sample t-test is that the two samples that we want to investigate, so we have two samples that we want to investigate, and we want to say something about whether the means are the same. So this is where you typically use a two-sample t-test. So your hypothesis is going to be something like the means are the same, and then your alternative hypothesis is going to be the means are not the same. So that's typically what the hypotheses are going to be when you're using a two-sample t-test. For the test statistic, because we want to figure out whether the population means are the same, what we want to do is we want to look at the difference between the two, and then we're going to be looking at a pooled standard deviation. Basically, we want to take some proportion of the first sample, and then we want to take some proportion of the second sample. And it's going to be given by this really nasty formula here. But you're not expected to know how to derive this or anything. You just need to remember it. And I believe your final exam would be open book anyway, so you can just open up your lecture notes and just memorize it or find it. So you don't need to memorize this. So the pooled standard deviation is just going to be whatever this thing here is. S1 and S2 are going to be the sample standard deviations that you have from your samples. And then N1 and N2 are going to be the number of samples from your specific samples here. And what you can see here is that your test statistic, it actually takes in a t-distribution, as you should expect, because we're dealing with a t-test here. So the degree of freedom is going to be n. So here we can kind of think about this as n1 minus 1. So remember that in the one sample, our t distribution was something like t of n minus 1. But because we're dealing with two samples, we're going to be taking in two of the samples here. So we're going to take in n1 minus 1 plus n2 minus 1. And then when we collect everything together, we get precisely n1 plus n2 minus 2. Yeah. So you don't need to memorize this. Just think about how you can go from one sample to the two samples. And they work pretty much the same way. Does anyone have any questions regarding this? No? Okay. And again, we can always construct a confidence interval. It's exactly the same as what we should expect. It's just going to be, the only difference is that this time, because we're dealing with whether the means are the same, the average mean is going to be x1 bar minus x2 bar. So we're going to be looking at the difference between the two, and then everything else follows the same. This is going to be your standard deviation. This is going to be the exact quantile as well. And that comes from your t-distribution. Cool. The second thing is, suppose that the two samples that we have are correlated. So the two samples that we have are related to each other, rather than they're completely independent of each other. In that case, what we have here is a paired t-test. So a paired t-test comes from the fact that the two samples have relations from one another. For example, a good example for this would be, say that you wanted to sample one sample. So you say that you had a sample from one team, and then you're like, okay, well, what do you think about this team before like a match? And then what do you think about this team after a match? So you can see that the two samples that we have are related to one another. And so as a result, we have a paired t-test. So because the two samples are not independent, we can't use the two sample t-test. And so we have to introduce what we call a paired t-test here. And the null hypothesis is going to be exactly the same, in that you're really going to be figuring out, well, you're going to be testing whether there's a difference between the two means. So you have x1 minus x2 equal to 0, and that's going to be the null hypothesis here. And then the alternative hypothesis is going to be, well, they're not the same. So there is a difference. The t-distribution here is going to be this here. So d bar is going to be, denotes the difference in the ith pair of the observation. So if you imagine, you have two columns here, and then you have like a bunch of data here. So say that you have 1, 2, 3, 4, and then you have 4, 3, 2, 1. Then the di is going to basically find the difference between these two things here. So you're going to be finding 4 minus 1, which is 3, 3 minus 2, which is 1, 2 minus 3, which is minus 1, 1 minus 4, which is minus 3. And then you're basically going to be summing up the average between these two, between all of these samples here. Yep. Now, this doesn't follow something like n1 plus n2 minus 2, because actually we only have one sample. It's just that we kind of talk to them twice. So here it follows an n minus 1 distribution, not one that depends on two samples. So it's going to work in exactly the same as you would expect when you had one sample. And everything else follows the same. So the only difference between the paired t-test and the two sample test is that you have slightly different test statistic because you're dealing with one sample rather than two. Pretty much the last one that you really needed to know is the chi-square test. So the chi-square test will determine whether two random variables are independent. So the null distribution is almost always going to be that the two variables are independent. And then the alternative hypothesis is always going to be that they are not independent. So we want to find evidence that they are not independent, assuming that that they are independent. So for this test, there's one thing that we needed to compute beforehand, and it's going to be the expected count here. So the expected count is just going to be the total of your row times the column total divided by the number of samples. So if you imagine that we had something like a table, we had something like 1, 2, 3, 4. So there are a total of two samples here. So x1, x2, y1, y2. Then you basically want to count the row total. So say that you want to compute this. Oops. Oh no. 4. So you basically want to compute this. That will be your row total. And then you want to compute, say, this. So you want to measure y1 against x1. You count this. Does that make sense? Yeah. And then the test statistic that you have here is just going to be the sum across all of the observed count minus the expected count all squared, divided by the expected count. And the expected count never changes. It's something that you would have already computed before dealing with the test statistic. Under the null hypothesis, though, the chi-squared will follow a chi-squared distribution with r minus 1 times c minus 1 degrees of freedom, where r is the number of rows that you have and c is the number of columns that you have. Yeah. So you have a bunch of different tests, and these tests, generally speaking, you should be able to know when to use it. So if you want to determine whether two things are independent, you use what we call a chi-square test. If you want to determine something about the differences between means, but you only have one sample, you use a pairs t-test. Otherwise, you would use a two-sample t-test. And then each of them will have specific types of test statistics as well. Does that make sense? Cool. So we have an example of a chi-square test here. So let's consider a simple random sample of 400 in all fields of employment. So we have this table here, and we want to carry out a test of whether employment area and gender are independent or not. So you look at this and you're like, okay, well, I have a employment area, I have gender, and I want to determine whether they're independent. So even if you weren't aware, you should be thinking, well, I should be using a chi-square test, right? Because you want to determine whether two things are independent. And we may assume that the observed chi-squared is 27.11. So we don't even need to work out what the observed value is. So your hypotheses are going to be that under the null hypothesis, you assume that they are independent, and then you want to find evidence that they are not independent. So these two are going to be your hypotheses pretty much almost always. I don't think you'll ever have a point where they're not the specific ones as well. So under the null hypothesis, we want to verify that the expected count of respondents. So basically the idea is that you want to compute the row total times the column total divided by the number of samples that we have here. So how would you compute, say, the expected count of employed in service and are female? So the idea here is that the expected count is going to be the row total times the column total divided by the number of samples. And then, yeah, so you basically get this here. Oops. So the total in service, right? If you go back to the table, so the total in service is 137, and 58. So the total number of people that are in service is going to be 137 plus 58. And then the total female is going to be 240. Here. Does this make sense so far? Yep. So what you basically want to find is the expected count here. So you do yeah, so you do the row total. So here, total in service, and then the total female, and then you get this result here. Cool. Okay, so the next part is to basically find the test statistic. So you want to compute it at the specific values. So we found the observed count. So we were given the observed count in the question, and we already computed the expected count in the previous part. And then we want to divide by the expected count as well. So here you basically just plug everything in, and then we spit out 3.42. And then the last step is to state the distribution that can be used to assess the significance. So it's going to be a chi-square test with degree, r minus 1 times c minus 1 degrees of freedom. Here, r is equal to the number of rows. So if we go back to the previous slide, it's going to be the number of rows. So it's going to be here. So it's going to be 3. And then here, it's going to be the number of columns, which is 2. And so if we compute this, we get 3 minus 1 times 2 minus 1, which is 2. So your degree of freedom is going to be 2. Yep. And then finally, we basically just compute the p-value. And once we compute the p-value, we state the conclusion given H0 and HA, which is your null and alternative hypotheses. Does this make sense? Yeah. So it works pretty much the same way. You basically just compute everything. You basically compute your p-value, and then you use your p-value to then write a conclusion about like whether you reject or you don't reject the null hypothesis. Okay, I'm just going to blitz through this topic. It's a fairly small topic as well, so I won't really go through this in depth. So the idea here is that you're given a bunch of data. So you're given a bunch of data here, and the idea is that you want to find the line that runs through all of the data that best fits all of the data here. So there are infinitely many lines that we can choose, but we want to choose the line that best fits the data here. And so there's multiple ways of looking at this. The first way is we're given a very general line, a very general equation for a line, and it turns out that the best line for this, the best line for any data is given by these coefficients here. So B1 is given by r times sy divided by sx, and B0 is given by y bar minus y1x. I won't go through the proofs of this because you don't really need to know the proofs for MATH1041, but you just need to know basically how to use these lines here. So r here is the Pearson coefficient, and these are your sample standard deviations based on x and y. In other words, this is basically what we get here. So it's going to be your mean plus any residual. And the residual is going to be basically the error that we get by using this specific line. So if we look at the distance to the line, so from a data point, the closest distance to the line is going to be the residual. And then we basically take the sum of all of the residuals here. Okay, and we can do the same thing for population as well. So instead of looking at, say, means, we can also look at a population, and it more or less works in the same way. And pretty much the last thing we want to look at is we can make inferences about a slope. So essentially, you can. So the idea here is that you can standardize this, and by standardizing it, you get that this actually follows a t-distribution with n minus 2 degrees of freedom. And then you can construct the confidence interval for this as well. Right? By using this, what we can do is we can also compute the hypothesis test to determine whether there is a relationship between these variables here. So under the null hypothesis, beta 1 equals to 0. So if beta 1 equals to 0, what that means is that there is no correlation between these two, because it doesn't depend on what x is. But if beta 1 is not 0, then there is some sort of correlation between y and x. And that's what we want to do when we're doing the hypothesis test. Cool. You can read this, but the idea here is that you basically want to find a line that minimizes all of the residuals. So here, if you have a bunch of data that kind of looks like that, you kind of want to find the line that best represents all of the data. And by determining all of the residuals, you can kind of look at how good this line is compared to other lines as well. Cool. And just to wrap up, we'll look at an example coming from 2018. So this is a lot of text as well. So let's try to kind of jot down the main points here. So you're given a random sample of 64 people. And the relationship between the reported hours of sleep during the previous 24 hours and the reported hours of sleep studied during the same period. So we want to report the number of hours that people sleep and the reported hours of study that people make. A linear regression model was fitted and some RStudio output is given on the next page. Use this RStudio output and plots provided to answer the following questions. So the first question is asking us about the relationship between sleep and study. And is the relationship between these two things statistically significant? So this is our RStudio output. So for the first question, what we want to do is we want to determine whether sleep and study have any correlation between each other or are related between each other. And so what that means is that we can conduct a hypothesis test to determine whether or not sleep and study are significantly are significant from each other. So here the idea is that we want to compute the p-value for the slope parameter, and we can do this by looking at the data that we're given. So here we can see that these are the coefficients depending on. So here we can see that there's study here. So this is in terms of our study parameter, and we can see that the p-value for our study parameter is 0.000954, which is very much statistically significant. And so what we can say is that there is very strong evidence for the slope being different to 0, because we are basically rejecting the null hypothesis. And for the null hypothesis, we always assume that the slope or the parameter for slope is 0. So for part A, we say yes, they are statistically significant. For B, so let's have a look at part B. So we want to write down the linear regression equation for predicting sleep from study. So the idea here is that we want to compute beta 0, we want to compute beta 1, and then any residuals that we have here. So if we look at this, the intercept, if we look at this, the intercept is going to be this value here. So the intercept is going to be 7.729440. And so what that tells you is that when you plug in x equals to 0, or when you plug in study equals to 0, then the intercept is going to be 7.7290, and so B0, so if we consider the line y equals to B0 plus B1x plus any residual, then B0 here is going to be 7.72940. B1 is going to be this value here. So it's going to be this value here. So that's going to be the coefficient of study. And so that's going to be what B1 here is. And then we have any residuals left. So we can kind of just set that equal to whatever it is. Does this make sense? So it's just to recap, 7.72940 is going to be the intercept. That's given by this guy here. Put it in. So the intercept, the coefficient of your intercept is going to be this value here. And then the coefficient of your study parameter is going to be this guy here. And so that's how you can work out what B0 and what B1 are. Okay? And once we have that, we can estimate the mean sleep if study is equal to 6 hours, and then we can also figure out what D is as well. So we want to basically look at what happens if study was equal to 6. So remember that study is our x value here. So it's the parameter that we're going to change. And so if study was equal to 6, then we can just substitute everything into this expression here, and then we can get sleeping 5.88842. So here, what we can do is we can just go x equal to 6, and once we get that, we get what y is, which is your sleep. And then lastly, we want to find what the rate of change of 1 unit is. So change in mean sleep for a 1 hour increase. So this is really just your B1 value here. So the B1 tells you roughly the rate of change at which y varies depending on x. So part D is simply going to be the coefficient of B1, which is going to be a minus 0.30683. Does anyone have any questions regarding that? No? Okay. That's basically the end of the workshop then. Thank you everyone for coming, and if you have any questions, feel free to ask as well. I'll stay back for a bit if you have any questions.